Most people are familiar with the big names in science: quantum mechanics, the theory of relativity, maybe even the multiverse. These ideas dominate documentaries and classroom discussions. But beneath the surface of mainstream science lies a hidden layer of theories, complex, lesser-known concepts that challenge even the most brilliant minds. That's where our focus is today. This isn't about rehashing what you've already heard. This is about ideas that push the boundaries of human understanding, the kinds of theories that don't show up in everyday conversations but are essential for unraveling the deeper mysteries of the cosmos. As we explore them, expect to be stretched, not just intellectually but philosophically, because these ideas don't just ask what the universe is made of, they question how we know anything at all. Now imagine a vacuum, empty space, totally silent, completely devoid of matter. In everyday life, nothing seems like a simple concept, but in the world of physics, especially quantum mechanics, nothing is anything but simple. What we call empty space is paradoxically buzzing with invisible energy. It's alive with fluctuations so rapid and subtle that they can only be described with math and imagination. At the heart of this idea lies a mystery known as the vacuum catastrophe. According to quantum field theory, the vacuum is not truly empty. It's filled with vacuum energy, a kind of background hum of activity that persists even in the absence of all particles. On a microscopic level, virtual particles are constantly appearing and disappearing in a blink of existence, creating a strange, jittery energy landscape in what we think of as pure nothingness. But when scientists tried to calculate how much energy this quantum vacuum contains, they hit a wall. The numbers they came up with weren't just large, they were astronomical. The predicted energy density was 120 orders of magnitude greater than what we actually observe. That's a number so large, it almost breaks the language we use to describe numbers. If the calculations were accurate, the universe as we know it simply couldn't exist. Matter would fly apart. Galaxies wouldn't form. There would be no Earth, no us. To make sense of it, think about designing a simple bridge. You do all your calculations based on the materials and structure, expecting it to support the weight of a car. Now imagine being told that your bridge could actually support the weight of the entire Earth. That's how absurd the discrepancy is, and yet it's very real. This puzzle is deeply tied to something called the cosmological constant, a term Einstein introduced when he believed the universe was static. He later abandoned it, calling it his greatest mistake, after the discovery that the universe is expanding. But as scientists began studying dark energy, the mysterious force behind the accelerating expansion of the universe, the cosmological constant came back. And here's the twist. Vacuum energy and the cosmological constant should, in theory, be connected. But they're not even close. This disconnect has left physicists scratching their heads. Some suspect our understanding of quantum theory is incomplete. Others think general relativity might be missing something. And then there are those who propose entirely new frameworks, like string theory or quantum gravity, to bridge the gap. But so far, no solution has resolved the mismatch. The implications are enormous. If vacuum energy were truly as high as predicted, the universe wouldn't be the calm, orderly place we see today. It would be in chaos, its fabric tearing apart with every passing moment. That it isn't means either the math is wrong or we're missing a fundamental piece of the puzzle. Either way, the vacuum catastrophe remains a powerful reminder that some of the biggest mysteries in science come from the places we least expect, even in the nothingness of space. And the puzzles don't stop there. Think about how we understand the movement of particles, tiny subatomic bits of matter that make up everything around us. In standard quantum mechanics, we don't actually know where a particle is until we measure it. Until then, it exists as a haze of possibilities, a wave of probability. This is the famous Copenhagen interpretation, and it's both fascinating and deeply unsettling. But what if particles always have a specific position and velocity, whether we measure them or not? That's the idea behind Bohmian mechanics, a lesser-known but thought-provoking interpretation of quantum theory. According to this view, particles are never truly uncertain. Instead, they follow precise paths, like marbles rolling along invisible tracks. The catch? These paths are guided by something mysterious called a pilot wave. This pilot wave acts like a hidden current, steering particles through space. Think of it like a canoe drifting down a river. Even if you don't know where the river twists or turns, the current does, and it carries the canoe along a specific path. In this analogy, you're not drifting aimlessly. You're being directed just below the surface of perception. That's what Bohmian mechanics proposes, that there's a deeper layer of reality, guiding every particle with mathematical precision. In contrast to the randomness of the Copenhagen view, Bohmian mechanics paints a universe that is ultimately predictable, at least in theory. If we knew all the starting conditions and could see the hidden pilot wave, we could, in principle, predict the future of every particle. This idea isn't universally accepted, and it raises tough questions about what can be measured, what is real, and how far our understanding can reach. But it's an elegant way to restore order to a quantum world that often feels chaotic. And perhaps in a universe where even empty space is filled with energy, the idea of hidden order isn't so hard to believe. In science, every theory is a lens, a perspective that helps us understand the invisible machinery of the universe. But lenses can blur as easily as they can focus. Bohmian mechanics, for instance, provides one such lens, sharp in some ways, yet contested in others. While it proposes a deterministic view of the quantum world, where particles follow definite trajectories guided by an invisible pilot wave, this idea doesn't sit well with everyone. One of the primary criticisms it faces is its reliance on something we can't directly observe, the pilot wave. For some physicists, this feels like introducing an unnecessary complication, an extra layer of reality that complicates rather than clarifies. After all, standard quantum mechanics, with all its strange uncertainties, already works remarkably well for making predictions. To add an unseen guide feels to some like patching a system that isn't broken. Yet for others, Bohmian mechanics is exactly the kind of clarity quantum theory needs. The idea that particles are always somewhere, that they have a real determined path, is comforting compared to the mind-bending probability waves of the Copenhagen interpretation. To those who find the randomness of standard quantum theory unsatisfying, Bohmian mechanics offers a framework that restores order to a chaotic realm. And more than just philosophical comfort, it proposes real answers to deep problems, like the infamous measurement problem. In most interpretations, observation causes a wave function to collapse into a definite state, a process that's always seemed vaguely mysterious. Bohmian mechanics removes that ambiguity. In this view, observation doesn't change the particle, it merely reveals what was already there. The interpretation takes its name from physicist David Bohm, who developed the framework in the 1950s. His work ran against the mainstream at the time, challenging dominant views of quantum behavior and opening the door to alternative ways of thinking. Though Bohmian mechanics has remained a minority view within the broader physics community, it has gained attention, especially among those looking for deterministic models or more intuitive explanations. For these thinkers, it's not enough that quantum mechanics just works. They want it to make sense. And even if Bohmian mechanics isn't the final answer, its value lies in broadening the conversation. It reminds us that current frameworks, no matter how accepted, are still incomplete. Our understanding of the quantum world remains a work in progress, and different perspectives might help complete the picture. The same hunger to resolve contradiction and confusion also drives inquiry into black holes, perhaps the most puzzling entities in the cosmos. Imagine holding a book full of characters, knowledge, and ideas, and tossing it into a black hole. From everything we understand about general relativity, that book and all its information is gone forever, swallowed by gravity so intense that not even light can escape. But quantum mechanics steps in with a hard rule: information, in any form, cannot be destroyed. And so begins one of the deepest paradoxes in modern science. A black hole is more than a region of intense gravity. It's a challenge to the rules we've come to trust. General relativity says that once something crosses the event horizon, the point of no return, it's gone. Meanwhile, quantum mechanics tells us that the properties of any particle, Its energy, momentum, identity must be preserved somewhere, somehow. These two principles don't agree, and yet both have passed every test thrown at them. Think again of that book. Classical physics says it's lost, but quantum theory insists the book still exists, not in the same form perhaps, but not destroyed. It's like watching a letter burn in fire. The ink smudges, the paper vanishes, but the information it held still lingers in the ashes, smoke, and heat. It's not obliterated, just transformed. If black holes can make that information disappear forever, then something about our most cherished scientific laws must be wrong. This paradox took center stage in the 1970s, when Stephen Hawking discovered that black holes aren't completely black after all. They emit radiation, now known as Hawking radiation, which slowly causes them to lose mass and eventually evaporate. But there's a catch. Hawking's calculations showed this radiation to be completely random. It carries no information about what fell into the black hole. So if a black hole disappears entirely, what happens to the history of all it consumed? Is that data lost? If so, the foundational rule of unitarity in quantum mechanics, that information must be preserved, is broken. And breaking that rule would shake the very bedrock of physics. It would mean revisiting everything we think we know about the universe. So physicists have spent decades searching for answers. Some suggest that maybe the information isn't truly lost. It's just encoded in ways we don't yet understand. Perhaps the information is subtly woven into the Hawking radiation, but hidden beneath layers of complexity we haven't yet unraveled. Others propose that it's stored on the surface of the black hole, encoded into the event horizon in a kind of cosmic data sheet, an idea known as the holographic principle. In this picture, everything that falls in is projected onto the surface like a 3D movie encoded in 2D. Still others suggest that black holes don't evaporate entirely. Maybe they leave behind remnants, strange objects that carry all the original information in some compressed, inaccessible form. Or maybe the paradox is pointing to something much bigger, a need for a new theory of gravity that fully merges it with quantum mechanics. In that vision, the conflict doesn't exist because we've simply been using the wrong tools to describe the universe. For now, no single answer satisfies every test. The black hole information paradox remains a brilliant thorn in the side of modern physics, a problem that refuses to be ignored. It lives at the crossroads of quantum theory and general relativity, where our current understanding falls short. And until we resolve it, we can't claim to truly understand space, time, or the nature of reality itself. Another concept that pushes us beyond traditional views is the idea that space and time themselves might not be continuous. The smooth-flowing space-time described by Einstein's equations could in fact be made of tiny, indivisible chunks, the basic elements of a framework known as causal set theory. What if everything we know about space and time, its smoothness, its fluid continuity, was nothing more than an illusion? That's the radical suggestion at the heart of causal set theory. It fundamentally challenges the seamless picture of space-time we've held since Einstein's theory of relativity first revolutionized physics. To grasp this concept, imagine looking at a high-resolution photograph. From a distance, the image appears flawless and continuous, but zoom in far enough and you'll see it's really made up of countless individual pixels. Similarly, causal set theory proposes that the universe, which seems to flow smoothly, is actually composed of discrete, indivisible points, tiny atoms of space-time. But these points aren't randomly scattered like specks of dust. They're intricately connected by relationships of cause and effect. Each element exists not in isolation, but as part of a greater web, where its position and existence are defined through its relation to others. Think of it like constructing a city. Each building represents a unit of space-time. These buildings aren't just floating alone, they're connected by streets, forming networks that allow one event to influence the next. In this analogy, the streets are like the causal links between events. One moment leads to another, like falling dominoes triggering a chain reaction. It's a dynamic structure where time flows and shapes space itself. In the familiar world governed by Einstein's relativity, space-time is a smooth, bendable fabric. Massive objects warp it, producing the gravitational effects we observe. This model works exceptionally well at large scales, from predicting planetary orbits to the motion of galaxies. But causal set theory suggests that this apparent smoothness is only valid when viewed from afar. Up close, at incredibly small scales, near the Planck length, which is around 10 to 35 meters, space-time might be granular. Just like zooming in on the surface of water reveals individual molecules, zooming into space-time might reveal a mosaic of distinct points bound together by causality. This idea doesn't just challenge our intuition, it aims to solve a central problem in modern physics, uniting general relativity with quantum mechanics. These two frameworks are both wildly successful in their own realms, yet they refuse to play nicely together. Causal set theory offers a possible bridge by suggesting that space-time itself is inherently quantum, made up of countable, discrete parts. If true, this quantum fabric of the universe could resolve some of the most baffling puzzles physicists face. One of those puzzles is time itself. In many interpretations of physics, time is treated as an emergent property, a feature that arises from deeper physical laws rather than something fundamental. But causal set theory turns that idea on its head. Here, time is real. It isn't an illusion. It moves forward, moment by moment, with each atom of space-time giving rise to the next. Think of building a wall, one brick at a time. Each new layer is laid upon the previous one, shaping the future step by step. This could offer a profound explanation for why time only seems to flow in one direction, from past to future, and never in reverse. Moreover, this granular view of space-time might help eliminate the troublesome infinities that plague theories of gravity. In general relativity, when we try to describe extreme environments like the center of black holes or the instant of the Big Bang, the equations break down. They produce singularities, places where math spirals into infinity and physics loses its meaning. But in causal set theory, because space-time isn't infinitely divisible, these infinities don't arise. Just like you can't zoom forever into a digital photo without eventually seeing the pixels, you can't dive infinitely into space-time without hitting its fundamental structure. Despite its elegance, causal set theory remains highly theoretical. We don't yet have direct experimental evidence to confirm or falsify it. Still, it's a bold and intriguing attempt to reimagine the very scaffolding of the universe. If correct, it could revolutionize how we understand not just gravity, but the nature of time, the origin of the universe, and the ultimate architecture of reality. Instead of seeing the cosmos as a seamless expanse, causal set theory invites us to envision it as a vast, interconnected tapestry of discrete events, a universe built not from continuous flow, but from the rhythm of cause and effect, moment by moment, atom by atom. At first, it might feel like you're simply wandering along a beach, picking up seashells at random, some close together, others far apart. But as you continue walking, patterns begin to emerge. The shells aren't scattered chaotically. There's a rhythm to their placement, a hidden structure beneath the surface randomness. The Riemann hypothesis functions like a map to that rhythm. If proven true, it would reveal the precise spacing of these seashells, the prime numbers, demonstrating that the seeming chaos of their distribution is in fact governed by a deep and elegant mathematical law. Why is this such a big deal? Because prime numbers are the atoms of arithmetic, the building blocks from which all integers are made. Understanding how they are distributed would revolutionize not just number theory, but mathematics as a whole, and the impact reaches far beyond the academic. Prime numbers are essential to cryptography, the science of protecting information. Modern encryption systems, like those used in online banking, secure messaging, and national security, depend on the difficulty of breaking large numbers into their prime factors. If we could unlock the hidden pattern of primes, it might change everything we know about digital security, for better or worse. Yet for all its potential, the Riemann hypothesis remains unproven. Mathematicians have verified that the first several billion non-trivial zeros of the Riemann zeta function do indeed fall on the predicted line, but a universal proof that confirms the hypothesis for all cases continues to elude even the greatest minds. Despite the simplicity of its statement, it has become one of the most challenging puzzles. in all of mathematics. In fact, it's one of the 7 Millennium Prize problems designated by the Clay Mathematics Institute, with a $1 million reward waiting for whoever cracks it. What makes it so elusive isn't that it's too complex to understand, it's that it connects to so many parts of mathematics. Algebra, geometry, analysis, and even physics all converge in this single problem. Some physicists have speculated that the Riemann hypothesis could be linked to quantum mechanics. The zeta function, central to the hypothesis, might be connected to the energy levels of quantum systems, a tantalizing possibility that points to hidden unity between mathematics and the physical universe. Though still speculative, this cross-disciplinary bridge highlights just how fundamental the problem might be. So, what does the Riemann hypothesis actually say? At its core, it's about where the zeros of the Riemann zeta function fall. These zeros are the points where the function's output is exactly zero. The hypothesis claims that every non-trivial zero of this function has a real part equal to 1, 2. It sounds technical, but what it really means is that there's a specific line, known as the critical line, in the complex plane, and all the meaningful zeros lie on it. If true, this would mean that the prime numbers are not scattered randomly, but instead follow a delicate, precise structure that we have only glimpsed so far. Imagine walking along that same beach again, now with a newly drawn map in hand. What seemed like random seashells before now align in patterns you couldn't see until you had the right perspective. That's what the Riemann hypothesis promises: clarity from chaos, order in the deepest layers of number theory. Now shift your attention from numbers to space and time. Another revolutionary idea in modern physics asks us to reconsider the very geometry of the universe, not just in terms of shape, but in terms of logic. Non-commutative geometry might sound technical or abstract, but at its core it's about questioning an assumption we rarely even notice, that the order in which we measure or act doesn't matter. In everyday arithmetic, 2x3 is the same as 3x2. That's commutativity. But what if there are situations where the order does matter, where changing the sequence changes the outcome? To illustrate this, picture a deck of cards. When you shuffle it, the order of the cards changes, and with that change, the whole outcome shifts. You might win the hand or lose entirely. In non-commutative geometry, space and time could behave like that shuffled deck. The order of interactions matters. The universe, on the smallest scales, may not follow the neat, reversible logic we're used to, but something fuzzier and more sensitive to sequence. This becomes especially important in the quantum realm. Classical physics allows us to know an object's position and velocity at the same time, but in quantum mechanics, things get weird. The Heisenberg uncertainty principle tells us that the more precisely we know a particle's position, the less precisely we can know its momentum and vice versa. This isn't just a limit in our measuring instruments, it's a fundamental property of reality. The very act of measuring one quantity disturbs the other. That's non-commutativity in action. Non-commutative geometry offers a mathematical framework to model this bizarre behavior. In this system, space and time aren't smooth backdrops. They're distorted, fuzzy, and deeply interdependent. Imagine plotting a point on graph paper. In traditional geometry, it doesn't matter whether you move along the x-axis first and then the y-axis, or the other way around. You'll end up in the same place. But in a non-commutative system, the path matters. Going up first and then left may lead you somewhere completely different than going left first and then up. The space itself responds to the order of movement. This revolutionary concept has real implications for theoretical physics. It could help bridge the gap between general relativity, which governs the cosmos, and quantum mechanics, which rules the subatomic world. These two pillars of modern science are currently incompatible. But if space and time themselves have a non-commutative structure at quantum scales, we may have found a unifying principle. Non-commutative geometry, in this sense, could form the backbone of a future theory of quantum gravity, a long-sought framework that explains how gravity works in the quantum domain. The theory has already found applications in string theory, a bold attempt to explain all particles and forces in terms of tiny, vibrating strings. In some versions of string theory, space and time themselves are non-commutative, meaning that the strings interact in ways that depend critically on the order of events. This opens up entirely new possibilities for how reality might be structured at the deepest levels. To ground it in something more relatable, think about reaching for a coffee cup. In the everyday world, it doesn't really matter whether you flex your fingers first or extend your arm. Either way, you'll grab the cup. But in a non-commutative universe, the exact sequence could make all the difference. Space itself behaves differently depending on how you move through it. These ideas may feel strange, but they open up new vistas in how we understand the fabric of the cosmos. Whether it's the hidden rhythm of prime numbers or the sensitive structure of space and time, both the Riemann hypothesis and non-commutative geometry reveal how much we still don't know, and how thrilling it is to chase the secrets that hide just beneath the surface of what we take for granted. And the way objects relate to each other becomes not just a detail but a determining factor. It's as if reality has its own internal shuffle, one where the sequence of actions fundamentally influences the outcome. In essence, non-commutative geometry provides a powerful lens through which mathematicians and physicists can examine spaces that break away from traditional geometrical rules. It gives structure to quantum uncertainty, helps model the behavior of subatomic particles, and might even redefine our understanding of the very threads that weave space and time together. Though it's still an evolving area of research, its implications are far-reaching. Whether it eventually leads us to a unified theory of quantum gravity or deepens our grasp of the cosmos, its influence is already reshaping how we think about the architecture of reality. Now, step into twister theory, an equally captivating framework that reimagines the fabric of the universe itself. Introduced in the 1960s by British mathematician and physicist Roger Penrose, twister theory is a bold attempt to bridge two of the most successful yet fundamentally incompatible pillars of physics, general relativity and quantum mechanics. Rather than working within the usual coordinates of space and time, twister theory builds its foundation on the geometry of light, offering an abstract yet potentially unifying way to understand both the very large and the extremely small. To make this idea more intuitive, imagine navigating through a city. In conventional physics, your location is a precise point on a map: latitude, longitude, time. You move from one point to another along well-defined streets. This is how general relativity imagines space-time, a smooth, continuous surface shaped by the presence of mass and energy. But twister theory flips that perspective. Instead of focusing on fixed points, it centers on the paths light would take through the city. These paths, called null lines or geodesics, are the essential building blocks of reality in this framework. In other words, rather than pinpointing where something is, twister theory is concerned with how events are connected by light. This shift may sound radical, but it offers a profound advantage. The major conflict between relativity and quantum mechanics lies in how they treat space-time. Relativity views it as a smooth fabric. Quantum theory suggests it's granular and uncertain at the smallest scales. These opposing views collide in extreme environments, like the core of a black hole or the very first moments of the universe. Instead of trying to mash these two incompatible views together, twister theory steps outside the problem and proposes an entirely new structure, one built on the relationships between light rays. At the heart of twister theory is a simple but powerful idea: use the geometry of light to define reality. In traditional spacetime, events are defined by 4 coordinates, 3 for space, 1 for time. But in twister space, the coordinates are replaced with twistors, mathematical entities that encode the direction and momentum of light. This approach simplifies many aspects of physics. By focusing on how light moves rather than where things are, twister theory distills the complexity of spacetime into a more elegant, interconnected form. One of the most promising applications of this theory has been in quantum field theory, the mathematical framework that describes how particles interact with one another through forces like electromagnetism and the strong nuclear force. These interactions often require impossibly complicated calculations. Yet, Twister theory has helped simplify some of these equations, especially in high-energy particle collisions. This isn't just theoretical speculation, it's a real practical benefit that has sparked renewed interest in what this framework could offer. To visualize Twister theory, picture yourself surfing a wave. Traditional physics would try to chart your exact position at every moment, like plotting coordinates on a map of the ocean. Twister theory doesn't care so much about those fixed points. It's more interested in the wave's flow, your movement across its surface, and the light that defines your journey. It's a shift from a static snapshot to a dynamic, light-driven narrative of motion and connection. In summary, Twister theory presents a fresh and elegant way of thinking about the universe. By emphasizing the geometry of light over rigid positions in space and time, it offers a potential path toward unifying general relativity and quantum mechanics. While the field is still developing, its simplicity, depth, and imaginative power make it one of the most compelling ideas in modern theoretical physics. It may not yet hold all the answers, but it's changing how we frame the questions, and in doing so, bringing us one step closer to understanding the true nature of space, time, and reality itself. When we begin to peel back the layers of geometry, something fascinating emerges, a world where dimensions are no longer confined to whole numbers. In this realm, called fractional or fractal dimensions, space itself takes on a different character. The usual understanding of dimensions, lines being one-dimensional, planes being two-dimensional, and cubes being three-dimensional, only scratches the surface of what's possible. But nature is rarely so neat. Many objects around us display complexity that doesn't quite fit within these clean numerical boundaries. They repeat patterns within patterns, each layer revealing more detail no matter how far you zoom in. That's where fractional dimensions come into play. To truly grasp this idea, let's begin with the basics. A line is one-dimensional. It extends in only one direction. A square has two dimensions, length and width. A cube adds a third, height. These are integer dimensions, familiar and intuitive. But now, imagine something that lives in the gray area between a line and a plane, more intricate than a line, yet not full enough to be called a true two-dimensional shape. This is where fractals step in, and one of the most famous examples is the Koch snowflake. The Koch snowflake begins as a simple triangle. With each iteration, smaller triangles are added to its sides, creating more and more detail. The process continues infinitely, though the snowflake lies flat on a surface, technically making it two-dimensional. Its endless intricacy suggests that it occupies more than two dimensions, yet it doesn't quite reach the third dimension. Mathematically, it has a fractal dimension of approximately 1.26, more than a line, less than a plane. This number reveals how much of the surrounding space the shape fills, especially as one zooms in closer. So how can something have a non-integer dimension like 1.26? The answer lies in how an object scales and fills space. A line stretches along one axis. A square covers an area. A cube takes up volume. A fractal, however, behaves differently. It's denser than a line, but too fragmented to be a full plane. Its dimension is a measure of this in-between state, a mathematical expression of how much space it actually occupies at different levels of magnification. This is especially apparent in nature, where complex patterns repeat at multiple scales. Consider the jagged outline of a coastline. From a distance, it may appear as a simple curve, but as you zoom in, more features emerge: tiny bays, inlets, and rock formations. No matter how much you magnify it, new details keep appearing. It's self-similar. Each part resembles the whole. The coastline, much like a fractal, doesn't fit neatly into one or two dimensions. It has a fractal dimension between 1 and 2 because it behaves more like a curve with depth than a straight line, yet it doesn't form a complete surface. This concept is not just beautiful, it's practical. Take the branching of trees, for instance. A tree starts with a trunk, then branches split off, and those branches divide again into smaller twigs. This recursive, repeating structure suggests that a tree fills space in a way that's somewhere between 2 and 3 dimensions. It's not just a flat diagram, but it's not fully volumetric either. Similarly, Your lungs and circulatory system follow fractal patterns to optimize surface area and efficiency. Blood vessels and airways branch again and again, reaching every corner of the body, all while packing into a confined space. Fractal dimensions help explain these structures and their efficiency. The brain, for instance, is packed with folds, called gyri and sulci, that increase surface area without increasing volume. This folding, much like a fractal, repeats patterns at different scales. Scientists studying the brain use fractal dimension analysis to assess the degree of folding and its relationship to cognitive function or neurological disorders. In conditions like schizophrenia or Alzheimer's, changes in fractal dimension can serve as potential diagnostic markers. Beyond biology, fractal geometry reaches into the vastness of space, the large-scale structure of the universe, the way galaxies cluster together and spread out across cosmic voids, has a fractal-like distribution. It doesn't follow a uniform grid. Instead, it resembles a web of interconnected clusters stretching across space in a pattern that's more complex than random scattering, but not perfectly ordered. By studying the fractal dimension of these galactic patterns, physicists gain insight into how matter is distributed on a cosmic scale. Even in everyday technology, fractal dimensions prove useful. Image compression algorithms, such as those used in JPEG formats, often rely on fractal mathematics. These algorithms identify self-similar patterns within an image, especially common in natural scenes like forests or clouds, and store them efficiently. Instead of saving every detail pixel by pixel, the algorithm saves instructions for reproducing repeating patterns. This reduces file size without sacrificing too much quality. And fractal dimension plays a role in determining how these patterns are recognized and reconstructed. To picture fractional dimensions intuitively, imagine slowly inflating a balloon. At first, it's a flat, two-dimensional disk. As it fills with air, it curves upward and becomes a sphere, a three-dimensional object. Now imagine if this transformation happened incrementally, in complex layers, with textures added at each step, so that at every stage the balloon occupies slightly more than 2 dimensions, but not quite 3. That's the kind of transformation that fractal objects undergo. They live in the spaces between dimensions, challenging the way we traditionally classify geometric forms. In conclusion, fractional dimensions provide a new language to describe complexity in nature and mathematics. They move beyond the limitations of whole number dimensions and capture the richness of patterns that repeat endlessly across scales. From the jagged curves of coastlines to the structure of galaxies, trees, brains, and even digital images, fractal dimensions help us see that the universe isn't built from perfect shapes, but from intricate, evolving forms. They reveal how deeply interconnected math and nature truly are, each offering insights into the other's hidden beauty. At the smallest imaginable scales, far beyond what we can see or touch, the very structure of space begins to behave in surprising and unfamiliar ways. Instead of being smooth and continuous as we often imagine it, space at this level appears to be made of discrete, indivisible units, much like how matter is composed of atoms. This idea forms the basis of an extraordinary concept in quantum physics: spin networks. A spin network isn't just an abstract diagram. It's a model that describes space itself as a web of interconnected elements. These elements are composed of nodes and links. Each node represents a quantum of space, a tiny grain, if you will. And each link between nodes carries a value of spin, a quantum property related to angular momentum. The term spin network arises from these very connections, which are more than lines. They hold information about how space is structured at its most fundamental level. What's truly remarkable and quite counterintuitive is the notion that space doesn't exist independently of these nodes and links. Instead, space emerges from the way these components are arranged and related to one another. Geometry, the shape and form of space, is no longer an unchanging backdrop, but something that is dynamically built from these quantum relationships. This shifts our understanding of the universe in a profound way. Rather than being a passive stage on which matter and energy act, space itself becomes a product of interaction, a byproduct of quantum connectivity. One of the most important and exciting applications of spin networks is found in loop quantum gravity, a theoretical framework that attempts to reconcile the laws of general relativity with the principles of quantum mechanics. General relativity, Einstein's legacy, treats space-time as a smooth, bendable fabric that responds to the presence of mass and energy. But this model starts to break down when applied to the smallest scales or to extremely dense objects like black holes. Loop quantum gravity attempts to go beyond this by suggesting that space-time itself is not continuous, but made up of tiny loops, and spin networks provide the mathematical and conceptual structure for this granular view of reality. In the context of loop quantum gravity, spin networks describe the geometry of space at the Planck scale, an unimaginably small distance where traditional physics no longer applies. These networks are not frozen or static. Just as Einstein's space-time could stretch, ripple, and curve, spin networks can evolve over time. The links between nodes may rearrange, and the spin values they carry can fluctuate. This constant shifting reflects the quantum nature of the universe, uncertain, dynamic, and always in flux. At this level, there is no fixed backdrop, no permanent space, only interactions and relationships that give rise to what we perceive as geometry. Perhaps one of the most radical implications of spin networks is the idea that space and time themselves are not fundamental. In classical physics, space and time are seen as absolute frameworks, unchanging arenas where events unfold. But from the perspective of spin networks, they are emergent phenomena. That is, they come into existence only when viewed at large scales, arising from countless microscopic quantum events. At the deepest level, reality might be composed of entities that have no spatial or temporal properties at all. Instead, these dimensions only become meaningful as a result of the collective behavior of these entities, much like temperature emerges from the random motion of countless molecules. This perspective leads to provocative questions. If space and time are not fundamental, what exists in their place at the most basic level of reality? What happens in extreme environments, like the heart of a black hole or the first moments after the Big Bang, places where traditional space and time seem to break down? Spin networks offer a possible way to explore these mysteries. They provide a mathematical and conceptual framework for describing the geometry of the universe, even in conditions where our usual theories collapse. They might allow us to peer beyond the boundaries of space-time and glimpse the raw architecture of the cosmos. In addition to these profound implications for our understanding of the universe, spin networks may also serve as a bridge toward unifying the fundamental forces of nature. In the standard model of particle physics, forces like electromagnetism and the strong and weak nuclear forces are explained through the exchange of particles called gauge bosons. Spin networks can potentially be extended to account for these interactions, weaving them into the same framework that explains gravity. This would represent a major step toward a unified theory of everything, a goal that has inspired physicists for decades but continues to remain just out of reach. Through the lens of spin networks, the universe begins to look less like an empty stage and more like a constantly evolving web of quantum relationships. Every grain of space, every connection between those grains, contributes to the structure of reality. Space isn't a passive void, it's an active participant in the universe's ongoing creation. And time? It too may be nothing more than a consequence of change within this quantum web. This idea is not only revolutionary, but it opens the door to entirely new ways of thinking about everything, from cosmology and black holes to the origin of reality itself. There's a revolutionary idea gaining traction among physicists, one that suggests the universe is far more strange and complex than we've ever imagined. It begins with black holes, the most enigmatic objects in the cosmos. Traditionally, black holes were thought to swallow everything, even light, leaving no trace of the matter that fell into them. But a principle now proposes something deeply counterintuitive. The information about the matter isn't truly lost. Instead, it may be encoded on the event horizon, the boundary of the black hole. This remarkable proposition leads to the mind-expanding possibility that not just black holes, but the entire universe itself could be described by information that exists on its outer boundary, compressed into a lower dimensional form. It's a radical shift from how we normally perceive the cosmos, yet it's one that many researchers are taking seriously. In recent years, this idea has evolved into even more intriguing territory, specifically, the possibility that space and time themselves might not be fundamental. Instead, they could emerge from something even more foundational: quantum entanglement. Entanglement is a bizarre but well-documented phenomenon in which two or more particles, once connected, remain linked across vast distances. The state of one particle instantly affects the state of another, no matter how far apart they are. This strange connection hints at something deeper, perhaps a hidden scaffolding beneath the observable universe. Physicists like Mark van Ramsdonk have suggested that the structure of space-time itself could arise from complex webs of entanglement. Imagine these quantum connections as threads, weaving together the fabric of space much like strands in a finely stitched tapestry. One helpful way to visualize this is through the image of a quilt. Each patch of the quilt is connected to those around it. These connections, when viewed together, form the whole blanket. In the same way, space may not exist as a singular continuum, but rather as a network of tiny patches stitched together through entanglement. The more entanglement exists between particles, the more extensive and connected space becomes. From this view, space is not something that simply is, it's something that happens as a result of these quantum interactions. It doesn't exist on its own, independent of matter and energy. It's the result of how they're related. This view of emergent spacetime suggests that what we experience, the vast stretches of cosmos, the ticking of time, the curvature of space, is a high-level illusion. The real truth may lie beneath, in the quantum structure that gives rise to it all. Like a hologram that seems to present a 3D image while actually being 2D, our experience of spacetime might be just a projection of deeper information embedded at a more basic level of reality. This comparison isn't just poetic, it's grounded in physics. Some theories suggest that the smooth, continuous nature of spacetime is similar to the surface of a frozen lake. It looks flat and solid, but at the molecular level, it's made of countless water molecules jostling in motion. In the same way, spacetime may be composed of discrete elements, fluctuating and interacting in a dance too small for us to detect. Digging deeper, this line of thought leads us to another profound realization. Perhaps the most basic building blocks of reality aren't particles, energy, or even fields. Perhaps they are bits of information. This is the foundation of the information universe hypothesis. It suggests that everything we see, touch, or experience can be reduced to binary choices, to questions and answers. This radical but increasingly supported idea reframes the entire cosmos not as a machine made of matter, but as a system made of information. It was physicist John Archibald Wheeler who famously encapsulated this idea with the phrase, "it from bit." According to Wheeler, every particle, force, or region of space ultimately derives its existence from an underlying bit of information. This concept transforms how we view reality. The universe, in this view, is no longer made of solid substances, but of choices, encoded in quantum states. Think of how a digital image looks smooth and continuous until you zoom in and see the pixels, each a tiny packet of information. Likewise, what we perceive as the smoothness of space or the passage of time might be the large-scale manifestation of countless tiny informational elements. If we could examine the universe at a fine enough resolution, we might find not waves and particles, but raw information, decisions encoded in the fabric of existence. The black hole information paradox offers one of the strongest arguments for the primacy of information. According to Stephen Hawking's discovery of Hawking radiation, black holes aren't entirely black. They slowly evaporate over time. But this process presents a puzzle. Where does the information about all the matter that fell into the black hole go? In classical physics, information cannot be destroyed. So if a black hole vanishes, does the information vanish with it? This would violate the very foundation of physics. One proposed solution is that the information isn't lost, but encoded on the event horizon itself, a thin boundary that holds all the data about what's inside. This idea feeds directly into the holographic principle, which proposes that all of the information inside a volume of space can be described by data on its boundary. Much like a hologram, a 3D image from a 2D surface, our universe might be a projection, a vast three-dimensional illusion arising from a much thinner, lower-dimensional layer of encoded information. What's even more astonishing is how this idea dovetails with quantum mechanics. At the heart of every quantum system lies uncertainty, and information is what resolves that uncertainty. When we measure a quantum system, we gain information about it, collapsing the ambiguity into a specific state. Quantum information, unlike classical information, can exist in superposition. It can be a mix of states at once. Only upon observation does it resolve into one possibility. Quantum entanglement, again, provides a crucial piece of this puzzle. Entangled particles don't exchange information through space. They are part of the same informational state. They act as one, no matter the distance. This instantaneous linkage seems to defy the classical rules of causality, but makes perfect sense if the universe is fundamentally informational. Finally, there's the idea that even the laws of physics themselves may be emergent. Just like a computer program runs according to rules written in its code, the universe might be running on a set of deep informational laws. These laws could change, evolve, or shift in ways we don't yet understand. Reality in this picture is not a fixed landscape but a dynamic computational process, a cosmic simulation of sorts, not in the science fiction sense, but as a network of ever-evolving informational processes. What we think of as constants or immutable principles could be local expressions of deeper informational dynamics. In this emerging view of the universe, everything, space, time, matter, even the laws of nature, may be emergent phenomena, rising out of the interplay of information. We are not merely inhabitants of this system, we are participants in its ongoing evolution, observers collapsing quantum possibilities into realities, decoding the cosmic message embedded in every interaction. It's a vision of the cosmos where the deeper we look, the less we find concrete things, and the more we uncover patterns of information, relationships, and logic. Reality as code, the universe as computation, existence as the unfolding of informational flow. The universe, as increasingly understood through the lens of modern physics, may not be the static, clockwork-like system once envisioned. Instead of being made purely of particles and forces interacting like mechanical components, a radical new perspective is emerging, one that sees reality itself as a vast, evolving network of information. Whether it's the encoding of quantum states, the behavior of black holes, or even the constants of nature, there's growing belief among physicists that everything we observe might ultimately be an expression of information. This represents not just a shift in theory, but a profound rethinking of what constitutes the essence of reality. One fascinating framework that supports this idea is known as quantum Darwinism, a theory that borrows from the principles of natural selection but applies them to the strange, probabilistic world of quantum mechanics. To understand it, we first need to grasp some of the unique features of the quantum world. In our everyday experience, objects have definite states. A ball is either here or there. A coin is either heads or tails. But quantum systems don't follow this logic. At their most fundamental level, particles can exist in a superposition, meaning they are in multiple states at once. Imagine flipping a coin and having it land both heads and tails simultaneously. That's the bizarre nature of quantum mechanics, where reality doesn't settle into a specific outcome until a measurement or observation is made. This brings us to one of the central mysteries in quantum physics. What causes this superposition to collapse into a single, definite state? This is known as the collapse of the wave function, and classical physics has no answer for it, because it assumes that systems always have definite properties. In the quantum realm, however, things remain uncertain until interaction occurs. Quantum Darwinism, a theory proposed by physicist Wojciech Zurek in the early 2000s, offers a compelling explanation. It suggests that the environment itself, plays a decisive role in selecting which quantum information gets retained and observed, and which information fades into the background, much like how evolution filters traits in living organisms. To visualize this, imagine a quantum system, say an electron existing in multiple potential states. When this electron interacts with its environment, light, air molecules, or other particles, it leaves imprints or traces of its state in that environment. However, not all aspects of its quantum information get preserved. Only certain robust properties, those less sensitive to disruption, survive and become accessible to observers like us. This process echoes the mechanisms of natural selection. Just as traits beneficial for survival are passed down in biological evolution, only the most stable quantum information gets copied and survives in the environment. A helpful analogy might be that of a forest filled with trees. Every tree interacts with the environment, sunlight, rain, animals, but only certain visible features, like the tree's height or the color of its leaves, stand out to a casual observer. The microscopic details of the leaf structure, while present, don't usually register. In the same way, the environment surrounding a quantum system acts like a filter. It amplifies and stabilizes specific properties, while the finer, more delicate details fade from visibility. What we perceive as a classical reality, a solid, stable world, is built from those selected and reinforced quantum characteristics that make it through this environmental filtering process. Take, for example, observing an electron at a specific location. In quantum theory, the electron exists in many possible positions until it is observed. But quantum Darwinism suggests that the environment has already chosen one of those positions for us by redundantly broadcasting it through multiple interactions, effectively erasing the alternatives. This explains why, even though quantum theory allows for multiple outcomes, we consistently see a single, definite one. The alternatives don't vanish in a dramatic collapse. They simply fail to propagate through the environment and reach our awareness. This theory provides a potential resolution to the infamous measurement problem in quantum mechanics, why we never observe superpositions like a cat being both alive and dead. It suggests that the universe operates much like a witness system. Every interaction between quantum systems and their environments sends out copies of information, much like several people witnessing an event and sharing the same version of the story. These redundant copies of information ensure that multiple observers, interacting with the same environment, will all perceive the same outcome. It's how the quantum world quietly gives rise to our consistent classical experiences. At a deeper level, quantum Darwinism helps explain how our familiar world emerges from the sea of quantum possibilities. The environment doesn't just randomly interfere, it actively shapes which versions of reality become tangible. This perspective further ties into the overarching idea that the universe is fundamentally informational. It's not that the world is built from particles that simply happen to behave in strange ways. It's that the very structure of reality may emerge from patterns of information being selected, copied, and preserved across time and space. And the implications extend even further. Consider the notion of supersolids, a phase of matter that challenges our intuitive ideas about how solids and liquids should behave. A supersolid flows like a liquid, yet maintains the rigid structure of a solid. On the surface, this seems contradictory. Solids retain shape because their particles are fixed in a regular lattice, while liquids flow because their particles move freely. In everyday experience, an object is either one or the other. But supersolids exhibit both properties at once, an astonishing quantum behavior where particles can simultaneously remain ordered, like in a crystal, while also moving without resistance, as if flowing through each other. One way to imagine it is to picture an ice sculpture that doesn't melt, yet somehow flows around obstacles like water. In this state, the atoms behave in ways that defy classical explanation. They are locked into position, but are also delocalized, part of a collective quantum wave that allows for frictionless motion. This coexistence of solidity and fluidity is only possible because of the quantum principles underlying it. Again highlighting that what we perceive as stable matter is, at a fundamental level, governed by quantum information. The discovery of supersolids is a powerful example of how new states of matter can arise from quantum behaviors that challenge our macroscopic intuition. It's yet another indicator that the universe doesn't conform neatly to classical categories. It's built on a foundation where information, entanglement, and probabilistic rules reign. As we continue to explore these strange frontiers of physics, we are not merely uncovering new facts. We are beginning to rewrite the very story of what reality is made of. The journey to uncovering the strange and fascinating world of supersolids began through the lens of another equally mysterious quantum phenomenon, superfluidity. Superfluidity, first observed in helium at temperatures near absolute zero, describes a fluid that can flow endlessly without encountering any resistance, an astounding behavior that defies our classical understanding of motion and friction. In a superfluid, particles move in perfect unison, behaving not as individuals, but as a single, coordinated quantum wave. This extraordinary property emerges purely from the principles of quantum mechanics, where the collective motion of atoms bypasses the typical forces that would otherwise slow or stop them. Supersolids take this strange behavior a step further by combining the structural rigidity of a solid with the frictionless flow of a superfluid. The idea that such a hybrid state could exist was once purely theoretical. In the 1960s, physicists speculated that if quantum effects could cause a liquid to become a superfluid, perhaps similar effects could cause a solid to behave in a similarly frictionless way. But this concept remained speculative for decades. There was no physical evidence for supersolids, nor was there a clear experimental method to create or identify them. That changed in 2004 when researchers experimenting with helium-4, a stable isotope already known for its superfluid properties, found signs that it might also exhibit supersolid behavior under extreme conditions. When helium-4 is cooled to temperatures just fractions above absolute zero, it can form a crystalline structure typical of a solid. Yet under such conditions, quantum mechanical effects become dominant. What researchers observed was that some of the atoms in this solid structure appeared to flow without resistance, just like a superfluid, despite the overall material retaining its solid lattice. This hinted at the formation of a supersolid, a state of matter that defied the traditional boundary between liquid and solid. This discovery was both groundbreaking and baffling. If the findings were valid, they meant that under extreme quantum conditions, matter could defy classical categorization and enter a new hybrid state. Further research and replication were needed, and in the years that followed, scientists refined their experiments, eventually confirming the existence of supersolids, not only in helium but in other systems as well. Each confirmation strengthened the idea that supersolidity was not just a theoretical anomaly, but a genuine phase of matter governed by quantum laws. To grasp how supersolids function, one must understand how particles behave in the quantum world. In classical solids, atoms occupy fixed positions within a lattice, locked in place by interatomic forces. But quantum particles behave differently. They can exist in a delocalized state, where their positions are not strictly defined but spread out over space. In a supersolid, this means some atoms stay fixed in the structured lattice while others move freely through it, without disrupting the overall order. The result is a material that retains a solid form, yet allows for internal flow without friction. Imagine a marching band arranged in a perfect formation on a field. In a traditional solid, each band member stands in their designated spot, never moving out of place. In a liquid, they would roam freely, the formation breaking down entirely. But in a supersolid, some band members move fluidly between positions, weaving through the others, while the overall formation remains intact. The structure is preserved, yet motion occurs within it, an elegant choreography governed by quantum principles. Supersolids open new doors in our understanding of collective quantum behavior. They demonstrate that even at macroscopic scales, where classical physics usually dominates, quantum effects can still play a decisive role. The phenomenon challenges long-held assumptions about the separateness of different states of matter and offers insights into many body quantum systems. complex systems where large numbers of particles interact in deeply interconnected ways. But beyond the intellectual intrigue, supersolids could hold real-world potential. Their unique properties, fluidity without friction combined with structural stability, make them a promising area for future technological applications. For instance, in quantum computing, materials that minimize energy loss are highly valuable. The resistance-free movement in supersolids could help in the development of ultra-efficient conductors or components that operate at near-zero energy cost. The possibility of frictionless materials could revolutionize industries where wear and energy dissipation are major concerns. Research into supersolids is still in its early stages, with many open questions about how these systems behave under different conditions or in varied materials. However, each new discovery pushes the boundaries of what we believe is possible in condensed matter physics. Supersolids highlight the remarkable versatility of quantum mechanics, revealing that nature can manifest behaviors far more complex and unexpected than previously imagined. As we delve deeper into the frontiers of quantum science, supersolids serve as a vivid reminder that the universe often operates according to principles that defy classical logic. They are not merely exotic states of matter. They are tangible evidence that quantum phenomena can scale up and reshape our understanding of the physical world. In the end, supersolids challenge our deepest assumptions and invite us to think differently about how matter behaves at its most fundamental level. Imagine being able to freeze time, not metaphorically but in a real physical sense. In the quantum world, this is not just science fiction. It's a demonstrable phenomenon known as the quantum Zeno effect. It describes something incredibly strange. By measuring a quantum system frequently enough, you can prevent it from evolving, effectively halting its natural progression, like stopping an atom from decaying simply by watching it. The idea may sound absurd at first, but in the strange and delicate framework of quantum mechanics, observation isn't passive. It's active, influential, and capable of fundamentally altering the fate of the system being observed. Let's start with a particle, say an excited atom that's about to emit a photon and decay to a lower energy state. Left alone, it will eventually do just that. But now imagine measuring it over and over again at incredibly short intervals. Something astonishing happens. The atom resists change. The act of observation collapses its wave function each time, resetting it to its original excited state. Essentially, it gets no opportunity to complete its transition. This isn't a mere delay. Under constant surveillance, the transition might never happen at all. The atom is frozen in place, as though time itself has paused within its tiny quantum world. This phenomenon defies our classical expectations of how time should work. In our macroscopic reality, time flows in one direction, irreversibly moving systems from order to disorder, from existence to entropy, from activity to decay. But in the quantum domain, this inevitability can be paused, stalled, even circumvented. The more frequently you observe the system, the less likely it is to change. This is the essence of the quantum Zeno effect. Change is suppressed not because of some cosmic interference, but due to the relentless act of measurement itself. But why does this happen? The answer lies in the peculiar nature of quantum measurements. In the quantum world, systems don't have definite properties until they're measured. Instead, they exist in superpositions, a blend of multiple possibilities simultaneously. The wave function, a mathematical description of this superposition, represents all the potential states a particle could occupy. When a measurement occurs, this superposition collapses, and the system chooses a single outcome. Frequent measurements, therefore, continually collapse the wave function before the system has had time to evolve into something new. The quantum system never gets the chance to explore the other possibilities. To visualize this, imagine playing a movie. You press play, and it starts. But each time you check it, it jumps back to the beginning. No matter how long you do this, the movie never progresses. The same happens in a quantum system under continuous observation. The story of change never unfolds. It's a stunning example of how fragile and reactive quantum states can be. Despite sounding like an abstract curiosity, the quantum Zeno effect has very real and practical implications, especially in the field of quantum computing. Quantum computers use qubits, which, unlike classical bits, can exist in multiple states at once thanks to superposition. But these delicate quantum states are vulnerable to noise and unwanted transitions that could ruin computations. The quantum Zeno effect offers a way to protect these states. By carefully monitoring qubits without fully collapsing their wave functions, scientists can stabilize them, reducing the chance of errors and maintaining coherence for longer durations. This kind of control is essential if we ever hope to build reliable quantum processors. Through the quantum Zeno effect, researchers gain a powerful tool, one that doesn't just observe a system, but influences it to remain in a desired state. It's as if you're babysitting the qubit so intently that it doesn't dare misbehave. The implications extend even further. This effect forces us to rethink the nature of observation and reality. In classical physics, observing a system doesn't change it, but quantum physics tells us that observation is an act of intervention. Watching a particle isn't like viewing a painting, it's like touching wet paint. You alter it by the very act of looking. The observer is not a passive witness. They become an integral part of the process, entangled with the system they're measuring. This interdependency raises profound philosophical questions. Does reality even exist in a definite way when it's not being observed? Is the universe fundamentally probabilistic, and our role as observers more active than we ever imagined? The quantum Zeno effect doesn't just suggest answers, it reshapes the questions entirely. In conclusion, the quantum Zeno effect is a stunning manifestation of the quantum world's non-intuitive rules. It reveals that time, change, and observation are not fixed and immutable as we experience them in daily life. Instead, they are flexible, responsive, and deeply intertwined in the quantum realm. From halting atomic decay to stabilizing the building blocks of future quantum technologies, this phenomenon is more than just a curiosity. It's a portal into the true nature of quantum reality, where the act of observation can quite literally stop time in its tracks. Now consider an idea even stranger: negative mass. In our everyday experience, mass is always positive. It's what gives objects weight, inertia, and presence in space. You push a rock and it resists motion, that's inertia. But what if instead that rock accelerated in the opposite direction? You push it forward and it moves backward. This is what negative mass would do. It's an object that behaves like it has anti-inertia. Instead of resisting motion, it accelerates away from the applied force, almost like it's rebelling against your attempt to move it. At first glance, this sounds like science fiction or a violation of the laws of physics. But it's not. The idea of negative mass is consistent with certain solutions in general relativity and quantum field theory. Though highly speculative, it doesn't contradict fundamental equations outright. The real weirdness comes when we explore how such mass would behave. Take Newton's law of motion. Force equals mass times acceleration. If mass is negative, then a force applied in one direction causes acceleration in the opposite direction. Now apply that to gravity. Normally, masses attract. The Earth pulls you downward. The Sun holds planets in orbit. But if one of the masses involved is negative, the interaction changes entirely. A positive mass would be attracted to a negative one, but the negative mass would be repelled. The result? A strange dance in which the two chase each other endlessly, the positive mass pulling closer, and the negative mass accelerating away faster and faster. This bizarre loop could theoretically create a kind of perpetual motion. Has negative mass ever been observed? Not directly, but researchers have simulated similar behavior in laboratory conditions. In 2017, physicists at Washington State University created a fluid of ultra-cold rubidium atoms that, when pushed, moved in the opposite direction, mimicking negative mass. While these aren't true negative mass objects, the experiment demonstrated how such behavior might manifest and opened new doors for exploration. If negative mass truly exists, it could unlock answers to some of cosmology's greatest mysteries. Dark energy, the mysterious force driving the universe's accelerating expansion, might involve negative mass. Some theorists suggest that pockets of negative mass scattered across the cosmos could generate repulsive gravitational effects, pushing galaxies apart. Likewise, wormholes, hypothetical tunnels through space-time, require exotic matter with negative energy density to remain open. Without such matter, they would collapse instantly. Negative mass could provide the stabilizing force needed to make interstellar shortcuts possible. Still, the idea remains controversial and difficult to work with. Negative mass often introduces paradoxes, including violations of energy conservation and thermodynamic stability. Yet in quantum mechanics, where counterintuitive behaviors are the norm, these problems may have solutions not yet fully understood. Whether real or simulated, negative mass challenges our deepest assumptions about motion, gravity, and the structure of reality itself. If confirmed, it would not only reshape our understanding of the universe, but potentially give rise to technologies and insights that seem impossible today. Just like the quantum Zeno effect, it reminds us that the quantum world isn't just strange, it's profoundly transformative, and it's only just beginning to reveal its secrets. Gödel took Einstein's equations and looked for a solution where the universe was rotating. This was not a hypothetical whim. He was exploring a mathematically consistent solution to the laws of general relativity. What he found was astonishing. In a rotating universe, the structure of space-time could curve in such a way that closed time-like curves would naturally form. These are paths through the fabric of space-time that loop back on themselves, allowing an object or even a person to travel into their own past. This was no trick of science fiction. Gödel's universe obeyed all the known laws of physics at the core for time. And yet it implied that time as we perceive it might be an illusion. In such a universe, the flow of time wouldn't be a universal arrow pointing forward, but rather a coordinate, a dimension that could bend and wrap just like space. The implications are staggering. If time can loop, then cause and effect blur. Free will, determinism, and the very meaning of change begin to unravel. Gödel's rotating universe was never meant to describe our actual cosmos. Observations show that our universe is expanding, not rotating. But his solution remains vitally important, not because it predicts our reality, but because it shows what reality could be under the right conditions. It proves that relativity doesn't forbid time travel. On the contrary, it permits it under certain circumstances. The barriers are not necessarily physical, but practical. The right configuration of mass, energy, and space-time curvature could, in theory, allow loops in time. Whether they can exist without creating paradoxes is still debated. But perhaps Gödel was after something even deeper. He was not simply constructing a thought experiment about time travel. He was questioning the objectivity of time itself. Gödel believed that time, as experienced by humans, is not an external physical reality, but a construct of human consciousness. In his rotating universe, there is no global time, no shared now that all observers can agree upon. Without such a universal present, the notion of time as a sequential, flowing dimension begins to collapse. This aligns eerily with certain interpretations of quantum mechanics, where time seems to behave differently at different scales, and the idea of a universal now vanishes entirely. It also echoes with philosophical traditions that regard time as an emergent or illusory feature of reality, not a fundamental one. In essence, Gödel's universe challenges us to re-examine our most basic intuitions. What if the past isn't gone and the future isn't yet to come? What if they simply exist, coiled and layered into the fabric of the cosmos, awaiting the right path to loop us back? What if our arrow of time is just the result of entropy increasing and not an inherent feature of time itself? These are not idle speculations. As we dive deeper into quantum gravity, cosmology, and the structure of space-time, questions like these will shape the next revolutions in physics. Gödel's solution stands as a monument to the power of thought, an elegant, uncomfortable reminder that the universe may be more flexible, more alien, and more fluid than we are prepared to accept. In conclusion, from the paradoxical stillness of the quantum Zeno effect to the inverted inertia of negative mass to the cataclysmic potential of vacuum decay, and finally the looping, timeless vision of Gödel's universe, one thing becomes clear. The universe we inhabit is far stranger than our senses or everyday experience suggest. At the smallest scales, reality is shaped not just by matter and energy, but by measurement, probability, and uncertainty. At the grandest scales, it is governed by warped geometries, hidden vacuums, and perhaps even time loops. The more we learn, the more we are humbled, not only by what we know, but by what we don't. Physics is no longer just a description of what is, but an exploration of what could be. And as we push further into these theoretical frontiers, we are reminded that our universe may not be the only way reality can be structured. Perhaps there are other valleys in the energy landscape, other loops in time, other states of existence that remain, for now, just beyond reach. But inch by inch, with theory, experiment, and imagination, we're getting closer. Imagine for a moment that time isn't the straight line we think it is, not a one-way track from past to future, but something far stranger, something that can twist, bend, and even loop back on itself. This isn't just philosophical musing or science fiction. It's a concept grounded in real mathematics and physics, thanks to the brilliant logician Kurt Gödel. Gödel genuinely believed that the universe could possess a kind of rotation, a cosmic spin so immense and subtle that it would fundamentally alter the behavior of time itself. In this rotating universe, as Gödel proposed, the fabric of space-time wouldn't behave in the predictable, linear way we experience daily. Instead, time would cease to be absolute and could actually curve back on itself. To grasp this, let's use a simple analogy. Imagine the Earth as a spinning sphere. If you travel long enough along its surface, you'll eventually circle back to where you started. Now replace the Earth with the entire universe, and instead of traveling across geography, imagine moving through time. Just as a traveler returns to their point of origin on Earth, in Gödel's rotating universe, one could return to an earlier moment in their own timeline. It suggests a truly staggering possibility, closed loops in time, where the future might circle back to the past. If time can loop, then our foundational understanding of cause and effect begins to blur. Actions and consequences no longer follow a strict order. Events could occur with no clear beginning or end, and you might even influence things that have already happened. This opens the door to paradoxes, such as the classic grandfather paradox, where one might travel back in time and inadvertently prevent their own existence. Gödel's model forces us to confront such scenarios, not as absurdities, but as legitimate outcomes within a particular cosmic framework. But it doesn't stop at paradoxes. Gödel's rotating universe also raises profound philosophical questions about free will. If time loops back on itself, does that mean everything is predetermined to repeat over and over again? Are we trapped in an endless cycle, simply playing out a cosmic script we're powerless to change? Are our choices real, or are they illusions within an eternal cycle? The notion that time might repeat invites us to reconsider the very nature of existence, choice, and destiny. Despite its theoretical consistency with Einstein's equations, Gödel's universe remains a mathematical curiosity rather than a physical description of our cosmos. Observational data tells us that our universe is not rotating in the manner Gödel envisioned. Instead, it is expanding. Yet the elegance of Gödel's solution lies not in its accuracy, but in what it reveals, that general relativity permits time loops under certain conditions. This insight has deepened our understanding of what time might be and how it might behave in extreme environments. Einstein had already revolutionized the concept of time, demonstrating that it could stretch or contract depending on speed and gravity. Gödel pushed further, proposing that time might actually fold back on itself. This possibility is difficult to visualize, yet mathematically valid. It shows that the universe's laws are flexible enough to allow realities far beyond what we experience. Gödel's work challenges not just science but also our perception. In everyday life, time is a constant, a ticking clock that never stops. But at a cosmic level, that constant may be an illusion. What if history isn't a straight path but a loop? What if progress, change, and memory are constructs our minds use to make sense of a reality that doesn't behave the way we expect? These are not trivial questions. They speak to the limits of human understanding when confronted with the vast, often counterintuitive nature of the universe. Gödel's rotating universe shows us that even the most familiar concepts, like time, may be far more complex and strange than we realize. His vision continues to inspire physicists, cosmologists, and philosophers alike, urging them to rethink time not just as a background for events, but as a dynamic participant in the story of the cosmos. And while Gödel's universe may not be the one we live in, it remains a powerful reminder that the truth about reality could be far more surreal than anything we've imagined. It invites us to think beyond clocks and calendars, to entertain the idea that time might not just flow. It might loop, twist, and rewind in ways we are only beginning to comprehend. As strange as this seems, Gödel's ideas paved the way for even more radical theories about time and the cosmos. One such theory, conformal cyclic cosmology, proposed by Roger Penrose, takes the idea of time's fluidity to an even greater scale. What if the universe doesn't just loop in time on an individual scale, but the entire universe goes through a cycle of death and rebirth? Conformal cyclic cosmology, CCC, suggests that our universe isn't a one-time event. Instead, it's just one phase, one aeon, in an infinite series of cosmic lifetimes. Like the mythical phoenix that burns and is reborn from its ashes, CCC envisions the universe dying in a state of entropy and then resetting into a new Big Bang. This new universe, this new aeon, carries forward the cycle endlessly, with no true beginning or final end. Penrose's theory stems from the idea that, in the distant future, as the universe continues to expand and cool, it will approach a state where all distinctions like time, space, and matter fade. When all matter decays and black holes evaporate, there are no longer meaningful units of time or length. The universe becomes conformal, meaning its shape can be transformed without altering its essential structure. This conformal geometry at the universe's end mirrors the geometry at the beginning. And when that symmetry is complete, a new aeon can begin, a new universe birthed from the final state of the old one. What's revolutionary about CCC is not just the concept of cyclical time, but the possibility that we might already have evidence of previous aeons. Penrose and his team claim to have found clues in the cosmic microwave background, the faint radiation left over from the Big Bang. They've identified concentric circles, which they believe are the imprints of ancient events like black hole collisions from a past universe. If true, these patterns may be the fingerprints of cosmic history repeating itself across aeons. While still controversial, CCC forces us to confront another radical possibility, that time itself, on the grandest scale, doesn't have a starting point. The Big Bang wasn't the first moment of everything, it was merely the latest in an eternal pattern, and just as each universe ends, another begins. Together, Gödel's rotating universe and Penrose's cyclic cosmology offer a glimpse into a reality where time is no longer fixed or linear. Instead, it becomes a canvas of endless possibility, curving, folding, and restarting in ways that stretch the imagination and challenge our deepest assumptions. In these visions, time does not merely move forward, it dances. What if the universe didn't just stretch endlessly into a silent future, but instead curved back on itself, looping time like a ribbon folded in on itself? That's precisely what Kurt Gödel, one of the most brilliant logicians of the 20th century, dared to propose. His theory wasn't just a quirky side thought. Gödel genuinely believed that the fabric of the universe could be rotating in a way that alters time itself. In this rotating universe, space-time doesn't behave the way we're used to. It starts to bend so drastically that time ceases to be absolute and can, astonishingly, curve back on itself. To make this idea more tangible, picture Earth as a rotating sphere. If you were to walk along its surface long enough in one direction, you'd eventually return to your starting point. Now take that same concept, but instead of walking over a surface, imagine traveling through time itself. Just as you'd come full circle on Earth, Gödel's rotating universe suggests you could come full circle in time, returning to moments in your own past. This isn't just an abstract idea. The implications are staggering. If time loops, then cause and effect, that bedrock of logic, starts to unravel. Events could occur with no clear beginning or end. You could travel backward in time and potentially influence your own history, maybe even prevent your own birth. It's here that we enter the realm of mind-bending paradoxes. Gödel's model doesn't just stir up questions about physics, it cuts deep into philosophy too. If time can loop, are our choices truly free, or are we trapped in some cosmic script, endlessly, repeating the same decisions in an eternal cycle? In such a universe, the very notion of free will becomes shaky. Are we living out choices, or simply playing out a looped sequence of events, unaware of the repetition? Gödel's rotating universe forces us to confront these uncomfortable possibilities. Despite being mathematically valid, Gödel's model doesn't match up with what we observe in the actual cosmos. Our universe doesn't appear to be rotating. Instead, it's expanding in all directions. But Gödel's idea still matters, not because it's an accurate description of reality, but because it shows what's possible within Einstein's equations. It reveals that time, as we know it, is far more malleable than the steady tick of a clock might suggest. Einstein showed us that time could stretch and contract under gravity and motion. Gödel pushed it further. He proposed that time might actually bend and reconnect with itself, forming loops so bizarre they're hard to even imagine. What Gödel achieved wasn't just a mathematical trick. He highlighted how limited our everyday understanding of time really is. His rotating universe may not reflect our own, but it exposes the vastness of what's possible under the laws of physics, and how small our view of reality might be in comparison. Gödel's genius didn't stop at logic and mathematics. He stepped into the domain of cosmology and reshaped our perspective on time and reality itself. Though we may never witness a universe like his, the thought experiment he gave us forces us to question everything we take for granted. Time might not simply flow forward, it might bend, twist, and even turn back upon itself, defying all conventional wisdom. And just when you think time's strange possibilities couldn't stretch further, another theory steps in, one that reimagines the universe not just as a loop, but as an eternal sequence of rebirths. It's called conformal cyclic cosmology, or CCC, proposed by mathematical physicist Sir Roger Penrose. Imagine for a moment that the Big Bang wasn't the singular start of everything, but just one chapter in an infinite book. According to CCC, the universe undergoes cycles, immense cosmic lifespans that eventually end, only to spark new beginnings. To grasp this, picture a phoenix, the mythical bird that burns into ash only to rise again. CCC treats the universe much the same way. After a universe ends in a state of maximum entropy, essentially a lifeless, spread-out void, it doesn't stay that way. Instead, time and space stretch so far that they become meaningless, and from this near-empty state, a new universe bursts forth. The death of one cosmos becomes the birth of the next. Penrose argues that, as the universe expands, its geometry becomes smooth and featureless, so smooth, in fact, that there's no longer a meaningful distinction between time and space. At that point, everything becomes conformal, meaning shapes and angles remain, but distances lose relevance. This allows the end of one universe to mathematically resemble the beginning of another. Thus, one cosmic aeon transitions into the next. This isn't just speculative philosophy. Penrose claims to have found hints of this process in the Itagen cosmic microwave background, the faint radiation left over from the Big Bang. He suggests that concentric rings observed in the CMB could be the scars of titanic collisions between black holes in a previous universe. These circles may be echoes from an aeon before ours, embedded in the very fabric of space. While CCC remains controversial, its implications are profound. It suggests our universe isn't the first and won't be the last. We may be just one link in an endless chain, each universe giving rise to the next in a never-ending cycle. That perspective doesn't just alter how we see time, it redefines the entire concept of cosmic history. Rather than a single beginning or an ultimate end, CCC offers a picture of eternity, a universe reborn endlessly, with each cycle leaving a faint whisper in the next. Now, while CCC questions how the universe evolves over time, another theory challenges how we understand one of the most fundamental forces in the cosmos, gravity. Traditionally seen as a basic force, gravity might actually be something entirely different. In 2010, Dutch physicist Erik Verlinde proposed the radical concept of entropic gravity, the idea that gravity is not a force but an emergent phenomenon. Like temperature, which arises from the collective motion of particles, gravity might simply emerge from the way space and information are organized. Think of it this way. Imagine pulling a rubber band. The tension you feel isn't from any fundamental force inside the rubber band, but from its structure resisting your pull. Verlinde believes gravity acts similarly. As particles move and entropy increases, the tension this causes in the information field of space gives rise to what we experience as gravity. This approach hinges on entropy, the universe's natural drift toward disorder. Where entropy is low, gravity seems to emerge as space tries to balance itself out. In a sense, gravity could be the universe's way of reorganizing itself, redistributing information to reach a more disordered and stable state. That's a sharp departure from Newton's apple or Einstein's space-time curvature. Verlinde doesn't deny their accuracy at our level of observation, but he suggests they may not capture the deeper truth. Tying into this is the holographic principle, the idea that all the information inside a space can be described by data on its boundary. Imagine a planet. Verlinde suggests gravity arises not from the planet's mass, but from information encoded on its boundary surface. If true, this might even offer new ways to explain dark matter, not as an unseen mass, but as an emergent property of information density in space. Though entropic gravity is still in early stages and faces skepticism, it forces us to reconsider what gravity even is. Not a fundamental force, but a byproduct, a reflection of how information spreads out in an evolving cosmos. Just like CCC and Gödel's model, it reminds us that the universe may not be what it seems. Our deepest intuitions about time, forces, and existence might all be grounded in a limited perspective. As science pushes those boundaries, we're invited to imagine stranger, bolder possibilities about the nature of reality itself. Imagine a universe not bound by a single origin, but one that breathes through countless cycles of death and rebirth. In most traditional models of cosmology, the Big Bang is regarded as the absolute beginning, the singular moment from which time, space, and matter burst into existence. But conformal cyclic cosmology, or CCC, disrupts this narrative. Proposed by physicist Roger Penrose, CCC reimagines the Big Bang not as the ultimate starting point, but as merely a transition, a doorway between the end of one cosmic epoch and the birth of another. To the average person, this idea can feel disorienting. After all, our experience of time is linear. Everything has a start and an end. But CCC invites us to think differently. It proposes that the universe is part of an eternal sequence of aeons, vast cosmic cycles where each universe ages, fades into a smooth state of emptiness, and then gives way to a new universe through something like another Big Bang. The idea is as poetic as it is radical. We might be living in the latest iteration of an infinite chain of universes, and just as ours was born from the ashes of one before, it too will eventually pass and give rise to the next. In this view, the cosmos never truly ends. Instead, it continuously regenerates, carrying faint echoes from previous universes imprinted in the fabric of space and time, like ancient footprints slowly fading into sand. These whispers, subtle clues from the universe before ours, may still be detectable in the cosmic microwave background. CCC may never be confirmed with absolute certainty, but the concept encourages us to expand our understanding of time, space, and continuity. It paints a picture of a universe with no true beginning or end, where time bends back on itself, looping endlessly through eons. For centuries, gravity has mystified scientists. From Newton's falling apple to Einstein's warping of space-time, our understanding of gravity has evolved through dramatic revolutions. But in 2010, a new and controversial perspective emerged, one that turned this fundamental force on its head. Proposed by Dutch physicist Erik Verlinde, The theory of entropic gravity suggests that gravity might not be a fundamental force at all. Instead, it could be a consequence, an emergent phenomenon resulting from entropy, the universe's natural inclination toward disorder. This idea seems almost counterintuitive. Gravity is the glue that holds planets in orbit and forms galaxies. Yet Verlinde proposes it's not an intrinsic interaction, but a byproduct of how information is distributed in space-time. Think of temperature. It's not a property of a single molecule, but an emergent result of billions of molecules in motion. Similarly, gravity might arise from the collective behavior of microscopic degrees of freedom, essentially from the way information behaves across the universe. Entropy is the core concept here. In thermodynamics, entropy measures the number of possible ways a system can be arranged, its disorder. A tidy room has low entropy, a messy one, high entropy. The universe, driven by the second law of thermodynamics, always tends toward higher entropy. Verlinde argues that as particles in space-time move and organize themselves, gravity naturally emerges as a kind of entropic force, not pulling objects together, but revealing how space-time responds to differences in information density. To picture this, imagine pulling on a rubber band. The more you stretch it, the more it resists. Verlinde likens this tension to the interaction between massive objects in space. As they shift and spread, they distort the information field of the universe, creating what we perceive as gravity. Space-time isn't being bent by mass in the traditional Einsteinian sense. It's rearranging itself to maximize entropy. Now, apply this concept to large-scale structures. Planets, stars, and galaxies don't warp space-time through an intrinsic force, but because of the way they alter the surrounding field of information. Gravity, then, isn't something objects emit. It's a response to the imbalance in the entropy field. And underlying all of this is the idea that information itself is physical, not just in the sense of bits and bytes, but as a fundamental element of reality, shaping how particles move, how systems evolve, and how the universe organizes itself. This notion aligns with another groundbreaking idea, the holographic principle. Originating from black hole physics, it proposes that all the information within a volume of space can be described by data encoded on its boundary. Much like how a two-dimensional hologram can display a three-dimensional image, in Verlinde's entropic gravity, this principle suggests that the force of gravity might arise not from the volume of a planet, for example, but from the information encoded on its outer surface. So picture a planet surrounded by an invisible shell of encoded data. As another object approaches, its movement is governed not by the planet's mass, but by the changes in this information field. This radically reframes gravity, turning it from a deep cosmic force into a side effect of how space-time seeks balance. Even more provocatively, Verlinde's theory could provide an alternative explanation for the elusive dark matter. Instead of invoking invisible particles, entropic gravity suggests that the anomalies we observe in galactic rotation, where stars move faster than expected, might stem from the underlying information structure of space-time itself. These patterns of gravity could be the universe's response to informational imbalance, rather than the pull of undetected matter. While entropic gravity is still highly speculative, it forces us to rethink gravity not as a fundamental aspect of the universe, but as a consequence of deeper, invisible processes. Processes that center not around mass or energy, but around entropy and information. Now let's extend this rethink of reality with another bold proposal: mirror matter. Imagine gazing into a mirror and seeing not just your reflection, but an entirely hidden world, one that mirrors ours in every way but remains invisible. This isn't science fiction. It's a serious theoretical idea suggesting that our universe might have a twin, a shadow version made of mirror particles. The concept stems from symmetry, a guiding principle in physics. Nature often favors balance, equal forces, matching patterns, mirrored behaviors. Yet one of the biggest puzzles in modern physics is the imbalance between matter and antimatter. For every particle of matter, there's supposed to be an equal antiparticle. And yet the universe is overwhelmingly made of matter. Mirror matter is one possible solution. It proposes that for every particle we know, electrons, protons, neutrons, there exists a mirror version. These mirror particles would interact with each other through mirror forces, but would barely interact with normal matter, perhaps only through gravity. This makes them almost impossible to detect, but their gravitational presence could explain phenomena we've long struggled with, including dark matter. Mirror galaxies made of mirror stars and planets could be surrounding our own. They don't emit light we can detect. Their photons don't interact with ours, but their mass exerts gravitational influence. In this view, dark matter halos around galaxies might be entire mirror galaxies, invisible but very real. Theoretical support for mirror matter isn't just wishful thinking. Back in 1956, the discovery of parity violation, where certain interactions favored left-handed particles over right-handed ones, shocked physicists. It showed that the universe doesn't always preserve mirror symmetry. But what if it does, on a deeper level? If a mirrored sector exists where right-handed particles dominate, then symmetry is restored, just not in a way we can directly observe. The mystery deepens when we consider the early universe. During the chaotic moments after the Big Bang, it's possible that symmetry broke unevenly, allowing regular matter to dominate our universe while mirror matter slipped into a hidden role. This could explain both the absence of antimatter and the presence of unseen mass. While detecting mirror matter remains a daunting challenge, the idea itself pushes the boundaries of how we think about symmetry, reality, and the unseen layers of the cosmos. It suggests the universe is far more complex and far more balanced than we ever imagined. What if everything we know about gravity isn't quite what it seems? For centuries, gravity has been understood as the curvature of space-time, a warping of the cosmic fabric caused by massive objects. Einstein's general relativity reshaped our understanding of the universe by showing that gravity isn't a force pulling objects together, but a result of how space-time bends and curves around matter and energy. But what if space-time itself isn't a smooth, continuous fabric? What if it emerges from something more fundamental, something discrete, like a quantum graph made up of countless tiny nodes and connections? That's exactly the idea behind quantum gravity, a bold theory that suggests gravity might not be a fundamental force at all, but a side effect of a deeper structure. In this framework, gravity emerges not from a cosmic law etched into the universe, but from the collective behavior of microscopic parts that form the geometry of space-time itself. Picture a vast web of quantum nodes connected by links. These dynamic relationships determine how distances and directions evolve, and from them, the illusion of space and time unfolds. Just like a city's roadmap emerges from individual streets, space-time could emerge from this invisible quantum network. As the graph evolves, connections shift, geometry changes, and what we experience as gravity is simply the result of this underlying structure adjusting itself. This shift in perspective is more than just an intellectual exercise. It might be the key to solving one of the biggest mysteries in modern physics: how to reconcile general relativity, which governs the large-scale universe, with quantum mechanics, which rules the microscopic world. These two frameworks have stood in tension for over a century, each describing reality in incompatible ways. Quantum gravity offers a possible bridge by treating space-time not as a continuous backdrop, but as something that arises from a more granular quantum foundation. Though quantum gravity is still speculative, it's not purely theoretical. There may be observable evidence hiding in plain sight. If space-time truly emerges from a quantum graph, then the transition from this graph-like state to smooth geometry would have left faint traces in the fabric of the universe. Scientists suspect that the early universe, shortly after the Big Bang, could still bear the marks of this process. The cosmic microwave background and the faint afterglow of the Big Bang might hold subtle irregularities or patterns that point to such a phase transition. Similarly, the arrangement and clustering of galaxies on vast cosmic scales could reflect the remnants of this quantum origin. Moreover, if space-time has a discrete, granular nature, then it should exhibit a kind of pixelation at extremely small scales. Just as a digital image appears smooth from afar, but reveals its pixel structure up close, space-time might behave smoothly at human scales, but show granularity at the Planck length, the tiniest scale in nature. Future experiments involving gravitational waves or ultra-precise measurements of cosmic phenomena might one day detect this graininess, offering indirect evidence that space-time and gravity itself emerge from a deeper quantum architecture. Quantum gravity doesn't just challenge our understanding of gravity, it challenges the very foundation of reality. It suggests that the smooth space we navigate daily is not a fundamental feature of existence, but the emergent product of something far more intricate. If proven correct, it would mark a major paradigm shift, reimagining the universe as a constantly evolving web of quantum connections, one where space, time, and gravity are not fixed entities, but outcomes of the universe's underlying code. Now consider another radical proposal, one that turns the idea of nothingness on its head. For most of us, the vacuum of space, the emptiness between stars and galaxies, is seen as a cold, silent void. But what if this nothingness isn't empty at all? What if the vacuum of space behaves more like a strange invisible fluid? Welcome to the world of superfluid vacuum theory, a daring concept that suggests the universe is permeated by a quantum superfluid. In classical physics, a vacuum is defined as the absence of matter, a space devoid of particles, energy, and activity. But quantum physics tells a different story. Even the emptiest regions of space are buzzing with fleeting energy fluctuations. Virtual particles constantly blink in and out of existence, creating a restless sea of activity at the quantum level. Superfluid vacuum theory, SVT, takes this one step further by proposing that this quantum vacuum isn't just active, it behaves like a superfluid, a special state of matter that flows without resistance. Superfluids are bizarre. When substances like helium are cooled to near absolute zero, they enter this exotic state. In this form, they can climb walls, flow endlessly through tiny cracks, and spin in vortex patterns that never decay. These properties defy our everyday intuition and hint at a deeper quantum order. Now, imagine applying this concept not to a tank of helium in a lab, but to the very vacuum of space itself. In SVT, the universe is filled with an invisible, frictionless fluid, a quantum ocean that underlies everything. This quantum fluid wouldn't just be a passive backdrop, it would be the medium through which particles move, forces operate, and space-time itself unfolds. In this theory, general relativity, which treats space-time as a smooth, bending fabric, becomes an approximation of how this superfluid behaves on large scales. Meanwhile, quantum mechanics, with its strange behaviors and unpredictability, reflects the interactions of particles with this underlying fluid at the smallest scales. To make this idea more relatable, imagine fish swimming in a river. The fish perceive the river as a still environment, but in reality the water is flowing, with currents, turbulence, and hidden eddies. The fish are affected by the flow in ways they don't fully understand. In a similar way, we humans live and act within the fabric of space-time, unaware that everything we do may be influenced by an underlying fluid we cannot directly detect. Perhaps the most astonishing implication of SVT is that what we consider fundamental particles, like electrons, quarks, or photons, may not be particles at all. Instead, they could be stable vortices or whirlpools in this universal superfluid. These localized disturbances would manifest with properties like mass, charge, and spin, not because they have them inherently, but because of how they twist and ripple through the surrounding fluid. In this view, particles are not tiny objects moving through space. They are the space, or rather, the structure of the vacuum itself, briefly organized into stable patterns. This idea mirrors other theories like string theory, which also views particles not as points, but as vibrations of a deeper entity. But SVT keeps us grounded in fluid dynamics, a framework more intuitive, perhaps, and one that could open new doors in unifying physics. If this model proves accurate, it might even shed light on the nature of dark matter and dark energy, the invisible substances that make up most of the universe. These phenomena, currently poorly understood, could be the result of behaviors within the superfluid vacuum on vast cosmic scales. Superfluid vacuum theory is still in its early stages. The mathematics are complex, and its predictions remain difficult to test. Yet the idea is compelling. It offers a unified picture where gravity, quantum mechanics, and the vacuum of space all emerge from a single, fluid-like reality. The universe in this vision is not an empty void, nor a rigid framework of forces, but a living, dynamic sea of quantum activity, quietly shaping everything we see. This theory dares to challenge some of the most fundamental assumptions we've held about space, time, and matter. By proposing that the vacuum of space behaves like a superfluid, a strange, frictionless medium, it gives us a radically new perspective on the cosmos. In this view, particles are no longer considered standalone entities drifting through an empty void. Instead, they are dynamic ripples, disturbances in a vast, invisible quantum fluid that permeates everything. If this idea is confirmed, it would represent a seismic shift in our understanding of reality, unveiling an entirely new medium underlying the very structure of existence itself. In another corner of theoretical physics, a concept known as the amplituhedron is turning heads with an equally revolutionary proposition. In the quantum world, particles don't interact in straightforward, predictable ways. Every time two particles collide, there are countless possibilities for how they might scatter and interact, branching into an overwhelming variety of potential outcomes. To make sense of this, physicists use Feynman diagrams, a complex system of lines and loops that map out each potential particle interaction step by step. While effective, this method becomes extremely cumbersome. As more particles and energy come into play, the number of diagrams grows explosively, making calculations massively time-consuming. The amplituhedron was introduced as a way to cut through this chaos. Rather than mapping every twist and turn of each interaction, this geometric structure allows physicists to encapsulate the entire process within a single, elegant shape. It's not just a helpful shortcut, it completely reframes how quantum interactions can be understood. Developed in 2013 by Nima Akani Hamed and his collaborators, the amplituhedron removed the need for space and time in these calculations altogether. In doing so, it suggested something profound, that space-time itself might not be fundamental. Instead, it may be a secondary consequence of a deeper, purely mathematical reality. To understand the power of this concept, imagine trying to describe a complex dance performance. Traditional methods would involve recording every move, every step, every beat, a frame-by-frame dissection of the performance. But the amplituhedron offers a way to view the dance as a whole, not as a sequence of movements, but as a complete and harmonious geometric expression. This object doesn't live in the familiar three-dimensional world. It exists in an abstract mathematical space. And yet, it can precisely describe the outcomes of real-world particle interactions with stunning efficiency. One of the most striking aspects of the amplituhedron is how drastically it simplifies quantum calculations. In traditional methods, the scattering of 8 gluons, the force-carrying particles that bind atomic nuclei, would require tens of thousands of Feynman diagrams. Yet with the amplituhedron, the entire problem collapses into a single, compact geometric formula. It's like replacing a mountain of paperwork with a single crystal that reveals all the answers just by examining its shape. This leap in efficiency isn't just a mathematical convenience. It speaks to something deeper, that the apparent complexity of quantum physics might be the surface ripple of a much simpler underlying structure. If such a clean, beautiful geometry can describe something as messy as particle collisions, then maybe the universe itself is built on hidden symmetries and elegant patterns we've only begun to uncover. Moreover, the amplituhedron raises challenging philosophical questions. If we can calculate interactions without using space or time, then is space-time truly real, or is it a construct? A useful illusion born from a more abstract set of principles? This notion echoes other areas of theoretical physics that suggest reality may be emergent rather than fundamental, that the universe we see is a projection of something more profound, encoded not in space and matter, but in pure geometry and relationships. Despite the breathtaking insights the amplituhedron offers, it's still a frontier of ongoing research. Scientists are exploring whether this geometric framework can be extended to include other types of particles and forces, and whether it might one day help in formulating a true theory of everything. A single unified framework that combines quantum mechanics with general relativity. The hope is that this mathematical object might do more than just simplify calculations. It might reveal the very code that the universe is written in. At its heart, the amplituhedron is a reminder that beneath the apparent chaos of particle interactions, there may lie a deep and unshakable order, a harmony that doesn't emerge from our traditional view of space and time, but from a deeper mathematical reality. It hints that perhaps the most accurate description of the universe isn't one written in fields and forces, but in angles, symmetries, and geometric perfection. Now imagine if this line of thinking could also unravel the dark mysteries of the cosmos, like the enigma of dark matter. For decades, astronomers have observed stars on the outskirts of galaxies moving far faster than expected. Based on visible matter alone, these stars should drift slowly, governed by the pull of gravity from the galaxy's center. But they don't. They race around their galaxies at speeds that defy Newtonian predictions. To account for this, scientists proposed the existence of dark matter, an invisible form of matter that exerts gravitational influence but doesn't emit or reflect light. It's thought to make up around 85% of the universe's mass. Yet, despite decades of searching, no one has been able to directly detect dark matter. So the question arises, what if dark matter isn't actually there? What if our current theories of gravity need revision instead? What if the universe isn't hiding mysterious invisible matter, but instead we've simply misunderstood how gravity works? This bold idea lies at the heart of a theory that dares to rewrite one of the oldest laws in physics. Known as modified Newtonian dynamics, or MOND, this controversial proposal turns our cosmic assumptions upside down. Instead of hunting for elusive dark matter to explain the puzzling behavior of galaxies, it suggests we take a closer look at the force we thought we understood best: gravity. To grasp why such a radical idea even came about, we need to revisit one of the most persistent puzzles in astrophysics, the rotation curves of galaxies. According to Newtonian physics, the gravitational pull on a star should weaken the farther it is from the galactic center. Just like in our solar system, where Mercury whips around the Sun quickly and Neptune drifts slowly in the outer reaches, stars farther out in a galaxy should orbit more slowly. But when astronomers began measuring the rotational speeds of stars across different galaxies, what they found didn't match up. Stars in the outskirts were moving far faster than Newton's laws would allow. Fast enough, in fact, that they should have flown off into space, no longer bound to the galaxy by gravity. And yet, they remained in place, orbiting steadily. This led to the now widely accepted explanation: dark matter, an invisible substance, undetectable by light, that provides the extra gravitational pull needed to hold these stars in place. It was an elegant patch, but still a patch, a workaround for a theory that didn't quite match the data. But not everyone was convinced that invisible mass was the answer. In 1983, Israeli physicist Mordechai Milgram offered a radically different perspective. What if, he proposed, the laws of gravity themselves begin to behave differently under certain conditions? Specifically, at extremely low accelerations, like those experienced by stars far from the center of a galaxy, the force of gravity might not decay as quickly as Newton predicted. This was the essence of MOND. Rather than introduce an entirely new form of matter to account for the discrepancy, MOND simply tweaked Newton's second law, suggesting that gravity itself grows stronger than expected in these fringe regions of space. This slight modification could elegantly account for the galactic rotation curves without needing dark matter. In MOND's framework, stars don't need an invisible gravitational helper to stay bound to their galaxies. The gravitational force they experience is just stronger than Newtonian theory would suggest at such low accelerations. And remarkably, this adjusted law has proven successful in predicting the rotational behavior of many different galaxies, especially those with minimal visible matter, where dark matter models often falter. To visualize the contrast, imagine trying to explain why a car is speeding along a racetrack. The dark matter model says the car must have an invisible booster attached, supplying extra force. MOND, on the other hand, suggests that the car's engine works differently than we thought. It doesn't need a booster at all. Under the right conditions, it naturally generates more speed. No need for mystery mechanics, just a shift in how we understand performance. MOND's appeal lies in its simplicity. With just a small revision to a foundational law, it solves a major astronomical puzzle that has plagued scientists for decades. Yet despite its elegant solutions, MOND has struggled to gain widespread acceptance, and for good reason. The biggest issue is that MOND works best on the scale of individual galaxies, but breaks down when applied to larger cosmic structures like galaxy clusters. These massive systems, composed of hundreds or thousands of galaxies bound together by gravity, seem to demand even more unseen mass than galaxies themselves. In these cases, MOND alone doesn't provide enough gravitational pull to account for observed dynamics, while dark matter-based models continue to hold up. Another major hurdle is theoretical compatibility. Dark matter comfortably fits into the standard model of cosmology, known as LCDM, lambda-cold dark matter, which integrates smoothly with Einstein's theory of general relativity. MOND, however, clashes with general relativity, making it harder to incorporate into the broader framework of modern physics. It lacks a universally accepted relativistic extension, which makes applying it to the early universe, black holes, or the expansion of the cosmos especially challenging. Even more problematic is MOND's failure to naturally explain the cosmic microwave background, the faint afterglow of the Big Bang. The temperature fluctuations in this radiation, as observed by satellites like Planck and WMAP, match the predictions made by dark matter models almost perfectly. These ripples suggest that invisible mass played a key role in shaping the large-scale structure of the universe. MOND, in its current form, does not offer a satisfying explanation for these observations. Still, despite these limitations, MOND refuses to be dismissed. Its predictive power in the realm of galactic dynamics continues to intrigue physicists, especially in cases where dark matter models show less precision. For some, it's not about MOND replacing dark matter entirely, but about the possibility that both perspectives may hold pieces of the truth. Hybrid models have been proposed, combining aspects of MOND with dark matter, or even exploring whether MOND could be a low-energy limit of a deeper, more comprehensive theory that includes quantum gravity. MOND has succeeded in keeping the conversation alive and forcing the scientific community to question its assumptions. After all, science thrives on challenge. Even if MOND ultimately turns out to be incorrect or incomplete, it serves an important role in pushing the boundaries of theoretical physics, ensuring that our models aren't just convenient but actually correct. In a field as vast and uncertain as cosmology, MOND represents more than just a theory. It's a bold act of intellectual defiance, a refusal to accept anomalies as unsolvable, and a call to rethink the very laws we take for granted. Whether MOND becomes a cornerstone of future physics or a stepping stone to something even greater, it has already achieved something remarkable. It's made us question gravity itself, and in doing so brought us one step closer to understanding the true nature